Good morning, everyone. It is my pleasure to be here for the second session of the Deeptails seminar. I remind you that the point of this seminar is to have a presentation that is more research-oriented, and this is combined with a more engineering-oriented discussion as well, so that we get to see exactly these details. The devil is in these details of so these are the details of these deep architectures that we are using all day long. Today we have a presentation that comes from Italy. So it is my pleasure to introduce Professor Elisa Ricci from the Department of Information Engineering and Computer Science at the University of Trento, and she's also the head of the Deep Visual Learning Research Group at Fondazione Bruno Kessler, and she's also a very good friend of mine, so I am very happy that she's presenting this. She's mainly interested in computer vision, multimedia, machine learning, and robotics, all these oriented towards the analysis of the automatic analysis of human behavior. Elisa will be presenting this with Andrea Simonelli, which is a second-year PhD student at University of Trento. So, of course, he is co-advised by Elisa Ricci, and the second advisor is Samuel Rotabouleau from Facebook. Together, they will be presenting a paper that they had accepted at ECCV last year. The paper title was Towards Generalization Across Depth for Monocular 3D Object Detection. So the floor is yours. I propose that we let them present for if you have half an hour or something like this. I mean, we can go a bit over, that's not a problem. And then we can have some question and answer session.
Okay, then. So, Xavi, thank you for the introduction. You hear me?
Yes, very clearly.
Okay. So, as you said, we are presenting a work that it's a collaboration between me and Andrea, that are affiliated by University of Trento and Fondazione Bruno Kessler, and a researcher from Facebook, in particular a team from the former Mapillary Research. We will talk today about our work on a specific topic, that is monocular 3D object detection. So this is the theme of the people that collaborate to this project. As I said, there is me and Andrea, and then Samuel, Lorenzo, and Peter from Facebook. Let me give you a bit of context. I will actually provide the context and some overview of our work, then Andrea will explain the details, okay? So we are interested in scenarios of autonomous driving. As you all know, the challenges that we have when we would like to have these vehicles that move in autonomy are manifold. And the challenges are, for instance, to be able to detect and track precisely all the objects that are present in the scene. These objects may have a different visual appearance, and we also interested in having models for accurate semantic segmentation. And we are interested in having the possibility to fuse wisely different type of sensors. I'm referring here in particular to LiDAR and cameras. In general, these images give you an idea of the variability of the scenes that you can see in autonomous driving problem. As I said before, we would like to develop technologies to achieve an holistic and semantic understanding of the scene. This means, with a specific reference to the work we are presenting today, that we would like to determine with some level of accuracy the position of all the objects present in the scene, as well as inferring their main properties. As I said before, and this is especially relevant for the presentation of today, the sensors that we are using to achieve this holistic semantic understanding of the scene are important because we may think about using expensive LiDAR sensors, or we may think about going for cheap alternatives such as simply using RGB cameras. The interest of many entities, I mean university companies, is very high in autonomous driving, as we all know. So the interest is not from the academia, but actually I would say that in the last few years the interest is mostly from research groups in companies and big companies like Waymo, Tesla, Toyota, and many more. Let me go a bit more in detail on the specific focus of our work. So we are interested in analyzing data from RGB camera, and in particular, not only not from many cameras. Actually, we would like to have a very difficult challenge. So we would like to be able to analyze data from a single camera, and of course, we would like to do some deep learning. So we need some GPU. Okay. But the problem we are addressing today is this one. It's called monocular 3D object detection. So we are having access to a single RGB image, and we would like to infer the 3 bounding boxes for all the objects present in the scene. As you may imagine, this is problem. It's very, very challenging and actually also ill-posed because we don't have access to depth information. But research in our community have gone very fast, and indeed recent work have shown that this is actually possible and with a high level of accuracy. So just to be a bit more concrete, I will show you a video of what we would like to infer. We would like to be able to infer, given an arbitrary scene, an arbitrary video stream, the 3 bounding boxes for all the type of object in the scene. So you will have 3D bounding boxes associated to cars, 3D bounding boxes associated to cyclists, 3D bounding box associated to pedestrians, and so on. So after I introduce the problem, let me provide you an overview of what we are going to present today. I will be a bit more formal in explaining what we mean by monocular 3D object detection. Then Andrea will illustrate in detail our work, as Xavi said, the work that was presented at TCCV last year. And in particular, Andrea will briefly introduce the motivation behind our work, and then our main 2 technical contributions. The first technical contribution is a new concept of virtual views that allows to simplify the problem of monocular 3D object detection. And the second contribution is a new architecture, a new deep architecture for the same task that we call MOVI3D. Of course, we will present results, and in particular, we will present results on the popular Kitty benchmark, where we, at the time of our submission, we were the best performance on the leaderboard. So let me be a bit more formal in introducing the problem of 3D detection. So you have a camera installed on your car, and you receive a video stream, you receive images. Actually, we are analyzing, we are doing an analysis at the image level, and we would like to use deep neural network, and we would like to compute 3D bounding boxes. What does it mean? So the computing 3D bounding box means inferring the center in the 3D world of this bounding box, means also inferring the shape and the orientation of this bounding box, so inferring the rotation with respect to the camera and inferring the parameters that tells you the width, the length, and the height of this bounding box. And the most challenging parameters that we like to estimate is distance. As I said before, this is the most challenging problem because we would like to infer distance from a single image. So in practice, we would like to have a neural network that are able to predict 4 groups of parameters. These are the parameters that define a 3D bounding box. So again, these parameters are a parameter that tells you the rotation with respect to the camera, and a set of parameters that tells you the shape of this bounding box. Here we denote them with S, and then some parameters that indicate the center of this bounding box in 3D, C, and then Z that indicate the distance of the object with respect to the camera. Which approach exists in the literature for 3D bounding box prediction? Of course, the best approaches, the most precise one, are the one who exploit LiDAR sensor, okay? LiDAR sensors are, they approach the deep architecture that process LiDAR sensor are very accurate because they can have information about distance, and so the distance estimation task is solved. On the other hand, these sensors are expensive, and we would like to see if we have a cheap alternative. Another obvious possibility is to use stereo camera rigs. This allows, as we all know, to use geometry to estimate the distance. However, they are not much widely used in autonomous driving. Besides this, they are also not cheap. That's why our community has started to look at monocular methods. So methods that try to estimate the 3D bounding box simply relying on cheap camera sensors. Of course, this is better in terms of costs of money, but this introduced the problem that the distance estimation is ambiguous because we would like to infer 3D information from two-dimensional data. Focusing on this last research area, so methods that use a simple single RGB images to detect 3D bounding boxes, I think that there exist mostly 3 ways of doing this, and we have indicated here one work for each of the possible strategy. So the first strategy is to have 2-stage detectors, similarly to the detection. This is a strategy that has been followed by Monodis, that is a method also developed by Andrea. And the idea of Monodis is to have a first stage where we estimate 2D bounding box from RGB images, and then a second stage where these 2D bounding boxes are used as input to part of the neural network in order to predict the bounding box in 3D. Another possible strategy, that here we report recent work at ICCV 2019 from Brazil and colleague, is to use single-stage architectures. This is actually the same philosophy that we adopted to the work that we are presenting today. The third possibility is to resort on the so-called pseudo-LiDAR methods. This pseudo-LiDAR method exploit existing architecture for monocular depth estimation to compute from RGB images depth maps, and then this depth information is projected into point cloud, and this point cloud are used by point cloud-based detectors to infer 3D bounding boxes, similarly to LiDAR methods. So basically, as I said, there are 3 main philosophies, and in this work we followed the second one. Before Andrea start to discuss in detail our work, we found it important to recap our contribution to the community in this topic. So first work from Andrea, it's the first version of the architecture that was called Monodis. In this work, there was a critical analysis of the state-of-the-art methods, and a new 2-stage 3D detector was proposed based on the concept of confidence prediction. And also a new metric was proposed for the Kitty benchmark that is now widely used by the community. This work was later extended into a PAMI paper, and experiments were carried out on large-scale datasets, and the method was extended to multi-categories. This method is also the winner of the camera-based New Sim Challenge at CVPR 19. Then there is the work that we presented last year at ECCV. That is the work that we will present later on today. As I said before, there are mainly two contributions: a new concept of virtual views that simplify the detection task, and then a lightweight single-stage 3D detector. We just released an archive paper where we instead propose a new pseudo-LiDAR approach based on 3D confidence, and we also perform a critical analysis of state-of-the-art pseudo-LiDAR methods, considering the Kitty benchmark, and in particular finding out and analyzing with a lot of experiments that there is a bias in the dataset, and so some work from our community is required to have a fairer protocol for comparing existing methods, and also to set the basis for a better comparison in future works. Let me give the floor to Andrea. We will go into the details, okay?
Can you see my screen?
Yes.
Okay, so thank you, Elisa. And as Elisa said, I will continue to go into the details of our ECCV work from last year, entitled Towards Generalization Across Depth for Monocular 3D Object Detection. So, as you've seen previously, we are dealing with monocular 2D object detection. So we have a single RGB image as input, and we have many issues. But the one which is the most critical is for sure the distance estimation of the objects, because we have a 2D input and we want to estimate a 3D measure, so the distance. So this is our main issue. And we have a working range, which is usually from 0 to 50 meters or up to 80 meters, for example. So another issue is that we usually use the full resolution image as input. So as you can see in this example image, the objects have very different scale, very different appearance. So this makes the whole detection very complex. The outcome of the learning process in the most optimistic way will be to have a generalization. So if you have, say, the same object across many distances, you will expect the network to generalize and to learn a representation which generalizes across distances. So if you have an object on 5 meters, the network can learn that representation. And if you see the very same object at, I don't know, 50 meters, the network, in the best possible outcome of the learning process, will use the same representation to say, oh yeah, that's the same object, and I will use the same representation. But in our studies, we learned that the network, instead of learning how to use the same representation across distances, prefer to memorize distance-specific representation. So if I have the same object on different distances, the network prefers to learn distance-specific representation. And this, of course, wastes the capacity of the network. So this is the issue that we want to tackle in this particular paper, because we want to help the network to generalize better across distances. And so by looking at what we had at disposal to deal with this problem, we understood that we had a lot of data that we were not properly exploiting. For example, we have the camera calibration, and then we have the camera position, so the 3D position of the camera, which captured all the images that we use as input, and in particular, its height with respect to the ground plane. And then we have a third thing, which are the dataset statistics. So we can exploit, of course, the objects annotation that come with the dataset, because we, of course, now we are dealing with supervised methods. So we have all the 3D annotations of the objects in the training images of the datasets. So the question is now, how can we exploit these priors that I just said? We can analyze the geometry of the scene. So if we take, as again, for example, this image, what can we say about this image? Just exploiting the priors. By this very nice animation, we can say that we can understand a little bit better this scene, so we can make our life easier. In particular, with the colors, we wanted to highlight that by simply exploiting the camera calibration as well as the camera position, we can define some distance ranges in which the objects are very likely to be. So if you see on the right, you see that there is a green, for example, from 0 to 5 meters. Then you have yellow and so on up to the red range. So we can exploit this to make the detection easier. So how can we do it? So let's suppose we want to detect the red car in the yellow range. How can we exploit the priors that I said before to detect it? So our intuition was to, we know how to move between 3D space and 2D image. As I said, we can exploit the camera calibration, camera position. So we can imagine to virtually move closer to the object. And we know that by moving closer to the object, the detection will be easier because the detection becomes more complex as the distance increases. So we can imagine to create what we call a 3D viewport, which is simply a rectangle in 3D space. So there are basically 2 points in 3D space that define a rectangle. And we can virtually place this in front of the object that we want to detect. So if we want to detect the dark red car, we can create the 3D viewport initially in a random position. And then we can move it virtually, of course, in front of the car. So now we created a 3D viewport that we place in front of the car that we want to detect. And how can we exploit this 3D viewport? We can exploit to detect the object, as I said, and help us to generalize better. So once we created the 3D viewport for the target object that we want to detect, we know the 3D position of the viewport, so we can project it onto the image and extract what we call a virtual view, which is on the right. So the virtual view, in this case, is the extraction of the 3D viewport on the image. And this extraction is very trivial because it only involves camera calibration parameters and a simple extraction on the 2D image. And once we extracted the 3D viewport and project it onto the image, we, of course, normalize it with respect to normalized size, if you want. So normalized 2D size. And this, we will see later, will help us to generalize better. So as I said, the objects in the virtual view now are normalized. So they look in particular as they were in front of the camera. And as I said, the car is now virtually closer, so the detection will become easier later on. And so this is our first contribution of the work. So we simply take the input RGB image, so the full resolution input RGB image, and from this RGB input, we compute a series of virtual views, one for each object. And you can see that in the full resolution RGB image, we have various distance ranges, and the scale of the object and the appearance changes drastically, while in the virtual views, the scale is normalized and also the appearance is normalized. Of course, there are some resolution issues, but these are not affecting the general learning capacity of the network. So this is our first contribution. So instead of using the full resolution image as input to your detector, you simply replace the full resolution image with virtual views, and we demonstrated to achieve higher detection accuracy with respect to previous methods. Our hypothesis is that, of course, by dealing explicitly with this distance issue, the scale issue, and the appearance issue, the generalization becomes easier. So the network has an easier way to generalize across distances. So let's compare, to convince you further, the two input representation that we have. So from one side, we have the full resolution image. So as I said, we have objects of different scales, and the working range is the full 0 to 50 or whatever meters, so 0 to 80 meters, in the sense that if you simply have the full resolution image and you want to apply 3D detection, then you have to apply, you have to detect objects from 0 to 50 meters, because it's the only time you have to detect. So this is what you have. But what about the virtual views? So as I said, the scale is normalized, the generalization is easier, but the most important thing is that we can further exploit the virtual view distance as an additional prior information to drastically reduce the working range of our detector. So if you want to detect the objects in the yellow range, there is no way in which I could detect the objects in the other ranges. But the point is that when we create the virtual views on the yellow range, we are explicitly targeting objects in that specific range. And we know that objects in that range are very likely to virtually appear as they were in front of the camera. And in addition, we have a prior distance of the virtual view. So in this case, say 5 meters. So our detector has not to detect the distance of the object in the whole working range as it was before here. But the working range is drastically reduced in the way that we have to detect only and regress the distance from the virtual view to the object, which is very reduced with respect to the full resolution image. So the estimation becomes easier. So if you are wondering if this is it, no, this is not it, because there is another detail here. So as I said, we can generate virtual views exploiting the object 3D annotation and the priors, which are the camera calibration, camera position, and the dataset statistics. But we have to make a distinction between the training phase and the inference phase, because maybe you already made the questions into your head, but we cannot exploit 3D annotation at inference phase. Otherwise, some people will get very mad with us, and we agree with them. So what do we do at inference phase? Because we don't know where the objects are. So yeah, as I said, at training phase, we know where the objects are. So there is no issue in making an object-specific virtual view. We know exactly how many objects are there, where they are, so we can put one of our virtual views in front of every object, and there is no issue. But we do it, as I said, by taking the 3D annotations. So we know the value of the Z, which is the distance of the center of the object with respect to the camera. And we create a virtual view, a 3D viewport, which is the one on the right, by defining the 2 points, which are simply very near to the object. And then we define a virtual view for each object without issue. And then normalize it with respect to the reference resolution. But what about the inference phase? Because as I said, we don't have the 3D annotation. So what do? It turns out that we don't really care where the objects are, because we found another equivalent solution to this problem. So we create what we call the distance-specific virtual views. So we know that we have to work from, for example, from 0 to 50 meters. This is our working range. So we create a series of distance-specific virtual views simply by discretizing this distance range. So we discretize it. We say, okay, we set a Z resolution of 5 meters, and we create a virtual views every Z resolution divided by 2, and we get what we have on the right here. So these are distance-specific virtual views in the sense that we extract from the input full resolution image on the left the bands which are corresponding to the specific distance ranges that you see in the middle. So as you would expect, going further and further distance from the camera, this distance bands becomes narrower, but then, as I said before, we normalize them, to a standard reference resolution. So by maintaining the aspect ratio, the narrower it gets, the wider it gets. So this is why the red band, for example, is wider than the one at the bottom, which is the nearest band. So to recap, at inference phase, we don't have the 3D annotations. We exploit a discretization of the distance range, and we compute a distance-specific virtual views. Then there is always the issue, okay, but inside this distance bands, we don't know where the objects are, but we will get into the detail later on. So this is our first contribution. And we demonstrate that using these virtual views is helpful to the 3D detection, but could be also helpful to the depth estimation, and in general to methods that need to estimate 3D measures from the 2D, if you have the calibration parameters available, of course. So if you're wondering, okay, you create virtual views, then you do the 3D detection, it seems quite slow. And this is not true, because we come up with a second contribution, which is a single-stage lightweight architecture. So a single-stage 3D detector, which is fully convolutional and is able to achieve a fast inference. So this is the architecture. As you can see, it's the first part is a widely adopted ResNet 34, and then we put a little FPN, which is simple 2 levels of the FPN, and then we fuse the information and we put that information as input to the last module, which is the 3D detection module. So as you can see, it's fully convolutional, and it can achieve very fast inference time. So we go from RGB values to outputs in a single stage. And this it's in contrast with the methods that Elisa was mentioning at the beginning of the presentation. So if you have the usual, 2D detector or 3D detector, which is 2 stages, then at the end of the first stage, you have always a slow region proposal, an NMS, and a ROI pooling operation. We slow down quite a bit the inference time. In this case, we don't have any of that because we have a single stage. The downside of this is that the training is tricky, because we need to train the 2D and 3D part at the same time. So if you have a 2-stage architecture, for example, you can dedicate the first stage to 2D detections. So you focus on 2D boxes. And then the second part, you can exploit some dedicated parameters for the 3D part. But in this case, we have the same parameters for the 2D and 3D. And as you can see, in the right part of the image, you see that we have the outputs on the top, which are the psi, so the confidences for the 2D and 3D. And then we have the theta for the 2D and 3D. And the same parameters are shared among the 2D and 3D. So this makes the training trickier. So going into the details a little bit of what we regress. As I said, we regress 2D and 3D boxes and 2D and 3D confidences. And every piece of the output is very important for the final outcome of the detection, in a sense that we have the 2D part, so we have the 2D boxes, and they are estimated in the most common, faster RCNN way, in the sense that we spread 2D anchors all over the image. And then with a matching algorithm, we know which are the positive ones, which are the negative ones. The positive ones, we regress them in a normalized way, in the faster RCNN way. Then we have a 2D confidence. Is estimated with the standard cross entropy across classes, or binary cross entropy if we have only positive and negative, and is always computed with respect to anchors. Then we have a 3D part, which is the most important. So as you've seen in the beginning of the presentation, we have to estimate 4 different things plus the confidence. So we have a center, which we estimate first in 2D and then is projected to 3D using the camera calibration parameters. Then we use the distance. And as I was saying before, we estimated with respect to the what is now capital Z VV, which is the Z of the virtual view. So what I was mentioning before, that the working range is drastically reduced, is that in a standard case, so without the virtual views, our network has to estimate a Z, what I call ZO, so Z of the object, which is from 0 to 50 meters. And in this case, we estimate a Z which is added with the Z of the virtual view. So the distance that the network has to estimate is only the distance between the virtual view and the object, which is much, much smaller than the distance from the camera to the object in almost all the cases. And the third thing that we have to estimate is the shape. So the width, length, and height of the objects. This is estimated in meters in 3D and is regressed with the mean object sizes. So we have some annotations. We know, for example, that a car is not 100 meters high and 1 kilometer long. We know more or less the object sizes. We can compute them from the training data set. We can compute mean object sizes and compute the final object size as a function of these estimates, which works much better than starting from 0 and regress them from 0 every time. Then we have the rotation, which is computed with respect to the camera and can be encoded in many ways. You can regress them directly. You can regress them with a mixture of classification and regression. What we thought would be the best way, and in the end worked best, is a combination of, so we regress the sine and cosine of the angle, and then recover the final angle with the arctangent of this estimate. Or, for example, in the nuisance dataset, which is a new and more complex dataset, the rotation must be estimated like in a fully general way. So the object can be rotated arbitrarily in 3D space. So we need to estimate a quaternion, and a quaternion is a very efficient way of estimating an arbitrary rotation. But this is just a matter of the parameterization of the rotation. So we can estimate from a rotation which is simply fixed to one axis with a sine and cosine, or a general rotation which is allowed by the quaternion. The last thing that I want to know is the confidence. So the confidence is basically an estimate of the quality of the 3D detection. So for example, in data sets like Kitty 3D or nuisance, or also all the other data sets that are developed to 3D object detection, you have to assign a confidence value to each box, right? So the most confident boxes will, of course, have more impact on the final score. So we find a way to estimate a 3D confidence, which is a direct measure of the quality of the regressed 3D boxes. And this is a very simple thing, but it works very well for us. So we simply estimate a loss for the 3D confidence, which is the negative exponent of the loss that we have for 3D. And we regress it with a simple binary cross entropy. And by obtaining this confidence, we can achieve much higher scores than without the confidence. So the last thing that I want to mention, another detail, is that we use InPlace ABN to reduce the memory required at training time. So if you have a network, which is very, very likely that you use the common sequence of convolutional batch normalization and ReLU, if you use this InPlace activated batch norm, which has been developed by Samuel, Lorenzo, and Peter at CPR 2018, they found a way to basically reduce the memory imprint at training time and halved it. So this is a very interesting and I think helpful way if you're dealing with memory issues at training time. I think you should check out their GitHub repository because they have a PyTorch implementation also for the latest PyTorch And the implementation and the modification to code are very, very negligible, I would say. So some more details, the last details. So for each input image, we generate 8 virtual views. And as I said before, we need to understand in the virtual views. So at test time, we compute the distance-specific bands. So in these distance-specific bands, we don't know where the objects are still, because at training time, we know where we are, and at test time, we don't know where they are. So we still need a way to estimate the position of the objects. So we compute some virtual views, and we set a probability at training time of, for example, 70% to generate a specific object view. It means that we generate with 70% an object-specific view, which actually contains an object. And then the remaining 30% of the times, we generate a view which doesn't have an object inside, or much more importantly, as an object which is in the distance bands that we don't know, we don't want to learn in that specific moment. So for example, if we generate a virtual view from the 5 to 10 meters band, and in that specific band there is visible an object which is 40 meters distance from the camera, we of course don't want to learn that, because we know that another virtual view will already cover that object. So in that specific case, we put that object to negative, and we will not learn on high confidence for that object. So another interesting detail is that, as I said, we compute these virtual views and we normalize all the virtual views to a reference resolution. This resolution is very small because it's 100 by 300, more or less, and is much smaller than the input. So the number of pixels is much, much smaller than the input. This allows us to go up with the batch size. In particular, with the full resolution image, we were using batch sizes which were much less than 100, and now we allow batch sizes of 2K. So in this case, we obtain a much faster convergence than usual, which is a very good thing. So let's see some numbers. Okay. So just to give you an overview of our results, we have the experiments on the Kitty 3D benchmark, which is the widely adopted benchmark. So every paper on 3D object detection has to evaluate on Kitty 3D. We have multiple classes, and we deal with them with a single model, trained once on all the classes. We use the official IUU thresholds for Kitty, and as Elisa briefly mentioned at the beginning, we use the refined metric which we proposed, and not the deprecated one. So we don't make any tricks. So these are the first numbers that we want to show. So this is the most important category in Kitty 3D, which is car. And as you can see, we have the bold numbers. So it means that our model, with respect to other models, achieve higher performances in a fair comparison. So for example, the M3D RPN paper uses a much deeper backbone. So it's denser to 1-to-1. And we use a ResNet 34 plus, as you said before, in the architecture, quite limited number of parameters in addition, but we achieve higher performances with respect to their method. This is the performance on the other two categories in Kitty, which are pedestrian and cyclist. As you can see, we achieve quite convincing performances on the pedestrian, and we don't achieve the best performances on cyclist. And I want to say that this is just, in my opinion, a problem which is found in Kitty, because the dataset is very, very unbalanced. So 75% actually of the annotations deal with car. Then we have another, I think, 15% on pedestrian, and the remaining are cyclist. So the cyclist 3D object detection in Kitty, it's in my opinion a very few shot learning, which we don't deal in any way. So this maybe justifies the reduction of performance on the cyclist. So in order to understand if these virtual views really make a difference with respect to using the full resolution image, we make a very direct and very transparent comparison. So we take a strong baseline, which is represented by one of these, so a method that uses a full resolution image as input, and we simply take that method, use the full resolution image, and obtain the first row of results. Then we substitute the full resolution image with our virtual views that are computed with a Z resolution of 5 meters, and we achieve higher performances. And these numbers tells us that the use of the virtual views by using the very same method increase the performances. And this, of course, justifies the use of the virtual views and make us think that the generalization with respect to distance is actually higher. As our hypothesis. We made another ablation, which is in a direct comparison with a competitive and alternative way of estimating the depth. So if you have, for example, the depth estimation to do, what you can do, you can regress a single number from 0 to 50 meters and expect the network to learn it and generalize well. Or you can do, for example, slightly smarter thing, which is regress the Z value, so the distance value, with a combination of classification and regression. So you simply discretize, as we did in the virtual views, the distance axis. So for example, you discretize with 5 meters, 10 meters, and then you have, as a first stage, you have a classifier, which has to determine in which bin your object is. And then you have another regressor, which has to regress the distance between the bin and the remaining distance with respect to the object. So we made this very direct comparison with the same discretization values that we have in our virtual views. And we demonstrated that we achieve higher performances if we use our virtual views with respect to a bin-based estimation, which is the thing that I just explained. Okay, this is just to say that we tried, of course, to discretize the distance axis in different ways. So we for example, use the discretization of 5, 10, and 20 meters. And we saw that the best performing method was with a Z resolution of 5 meters. As a last ablation study, we wanted to understand really the generalization capabilities of our network. So our theory is that our network can generalize better across distances, but is this true? So we thought about an ablation study that would show this in an explicit way. So as I said many times in this presentation, we have a distance range, which can be from 0 to 50 meters. So we said, okay, let's split this range in half. One will be our testing range and one will be our training range. So for example, in this image, we show that the testing range is in the near to middle, and then the testing range, the training range is from middle to far. And so we tested on non-overlapping object ranges. And this table shows that the generalization of our network with respect to another baseline, which is the monodisk baseline that we shown before, achieves an order of magnitude higher performances with respect to that baseline. So it means that, for example, in the first line, in the first 2 rows of the table, we tried to train on far images and validated on near images. Then we switched, and then we also computed the last 2 rows, which are training on near and far, and validated on middle. So you would expect also the detector trained on the full resolution image to achieve good performances, but this was not the case. While in our proposed method, so the MOVI3D in the very last row, we achieved very good performances. So this means that generalization with respect to distance has been achieved, and the generalization is better than before. So we have some qualitative results of our method. So you can see at the bottom, you can see the RGB image with the 3D detections, which are the green boxes. The number that you see there is the final confidence of our detector. at the top, you can see the very same scene, but it's basically rendered as a point cloud. So we took the RGB information from the bottom and we render it at the top, but we render it in a way that our 3D results were much clearer, because we put the camera a little bit higher and tilted a little bit down, because you can see that usually in this monocular 3D object detection, if you only look at the detections on the RGB image at the bottom, you cannot really understand if they are precise or not, because the distance, as we always said, is a nilpoise problem. So you don't know if the rectangle is actually at the right position with respect to the distance. So in the top, we wanted to show this. So we put the camera a little bit higher and tilted a little bit down. So you can see that the boxes that we show at the bottom are actually around the objects, also around the real distance of the objects. Okay, so I think this is it. Of course, if you have any questions, you are more than welcome to ask them now or to write me an email anytime.
Hi. Thanks for the presentation. Let me just stop the recording, and I think there will be some questions from the audience.